Hello and welcome to the next session of Academic Crisis Line. Today we're going to give you a practical introduction to linear mixed effect models, and with me, apart from me today, the wonderful Dr. Stacey Humphreys is giving the tutorial today. There's a bunch of information in the bottom of this video. There are links to my Open Science Framework archive for this entire study where you can download the data, all the code we are using today, as well as additional information to the study. You also can find the link to my website and the Academic Crisis Line website, where you find more information about previous sessions, maybe upcoming sessions, and also a link to vote for topics you are interested in. If you voted before, no worries, you can vote as often as you want. So in order to interact with us or ask questions during the sessions, which you can do all the time, please don't wait. There's a tiny delay between us talking and you listening to us. So please don't wait with your questions to the end, because we're sitting here awkwardly waiting for questions and you might just be late. This is weird. Just ask them right away. And in order to ask questions, you can either use the YouTube chat function here on the right side of the screen. There, you can just type, once you're logged in with your Google Mail account, you can just type in and ask questions and interact with us directly. And there also reposted a link to the Open Science Framework where you can download the data. The alternative way to contact us is to tweet to @ph_dial. There you can just, if you send a message to me there, I will answer live during the session. If there are questions after or clarification or suggestions about this series, you can email me at fhartung@upenn.edu. And of course, visit my website, storiesinthebrain.com, where within the next hour there will be a summary and more information about this series. All right. So quick before we start, I walk you through my Open Science archive because it's very important that you understand how the materials work. So quick screen share. Here. So this is the Tim and Tom project, asking the very important research questions, whether Tims are hot and Toms not. And this was a study I did many years ago as a graduate student with some friends of mine. We recently decided to publish this, so we wrapped this all up and brought this into publishable format. It's a study where we wanted to investigate whether vowel quality in first names has an influence on how attractive we find the bearer of the name. When you scroll down under the information of the study, you find the archive with the files here. There's the preprint of the study if you want to read more, all the study materials. And in the study materials, there's also a link which says Linear Mixed Effect Models Tutorial. If you open this, this contains 2 files. Please download new. And there you get a doc file in which all the text for my code and the output of the model is saved. You can copy all of this and paste this right into your editor window of your RStudio desktop, and the data is here under data. It's data _Tim Tom final. You can just download this, and then you have access to everything you need for this session. So now, I'm handing the session over for Stacey, who is going to give a theoretical overview and introduction about what the conceptual background is and why you should do linear mixed effect models instead of an OS and t-test in certain instances, and where it's useful and why not.
Thanks, Francisca, and thank you so much for having me today. I'm excited really to talk about linear mixed effects models today because this is something that I have also recently learned how to do. And I think that I had a lot of questions and concerns at the beginning that I feel are common to everybody who's just starting out. And so we can talk through lots of those questions today. So for me, the top 5 questions that I think people encounter a lot when they first are starting to run mixed effects models The big first one is, why is a linear mixed effects model better than an ANOVA? Secondly, what are fixed and random effects? What is a random intercept and a random slope? Should I include random slopes into my model? And how can I tell if my model predictors are significant? We're going to answer all of these questions first, and then Francisca and I will show you how to actually run the models in R and talk through what the output means. So in psychology, we're all used to doing ANOVAs, and only recently have people started to use linear mixed effects models. The first person to realize that there might be a problem with what we're doing was Herb Clark, and this was all the way back in the 70s. And he published this great paper, The Language as Fixed Effects Fallacy. And he wrote that language researchers are often assuming that their findings generalize beyond the stimuli that they're using in their experiment, and this is probably false. So if you are testing how people comprehend nouns and verbs, and you use 30 nouns and 30 verbs in your experiment, you're assuming that the results generalize beyond this particular sample of items, and this is probably not true. So Clark argued that in our analyses, we've got to take into account the variability that is due to the items, as well as the variability that is due to the participants. And he advocated that people actually run two ANOVAs. So firstly, one where they average over items for each subject. This is the ANOVA that we're all used to doing. And a second one where they average over subjects for each item. And based on these two ANOVAs, you could calculate an F kind of ratio statistic. This was kind of complicated to do, and so people just didn't really do it. They liked calculating the two different ANOVAs, but then it was pointed out that even if you get a significant result in both of these two kinds of ANOVA, it's still not enough to generalize. And on the basis of this, the Journal of Memory and Language at this time, so around 1999, required authors to start reporting this F ratio statistic, but it was kind of complicated for people to do. And finally, in 2006, Harold Bayen just said, this is too complicated, this two ANOVAs thing, let's switch to mixed effects models. And this was kind of where the revolution began. So the first big question is, what is mixed about mixed effects models? So in an ANOVA, we have only what are called fixed effects. And in a mixed effects model, we have both fixed and random effects. And so let's think about what these terms actually mean. So a fixed effect means that the levels of a factor that exists in your study constitute the entire population of levels that you want to generalize to. So you may have a fixed effect of word type in your study. You might be interested in nouns and verbs, and you don't care about generalizing to other kinds of words like adjectives or prepositions. You only care about nouns and verbs. A random effect means that the levels of the factor that exists in your study represent just a sample of the population that you would like to generalize to. So you probably would want to have a random effect of subject. You want to be able to generalize from this sample of people in your study to the population of all people. You might also want to have a random effect of item. So you might want to generalize, for example, from this sample of words that I used in my experiment to the population of all words. So usually when we're deciding whether or not a variable in our study is fixed or random, this really only applies to the levels of categorical predictors. So remember that subject and item are both categorical predictors. Continuous predictors are typically measured characteristics of subjects or items, and therefore they're usually considered fixed. So people are often asking, is this variable in my study fixed or random? And there's often not just one answer to that question. You might be able to treat the same variable as fixed or random depending on how you do the analysis. So you need to think through what you want the analysis to tell you. So if you specify a variable as fixed, you're going to get individual parameter estimates for each level of the factor. And that means that each level of the factor is eating up a degree of freedom in your analysis. If you specify a variable as random, you're going to get just the population variance associated with the whole factor. So the whole factor only uses up 1 degree of freedom in your analysis. So in practice, we usually want individual parameter estimates for each level of our categorical factors. We want to know, for example, how the two levels of word type affect reaction time differently. So most of the time, the conditions that you've manipulated in your experiment are going to be fixed factors. On the other hand, we usually don't want individual parameter estimates for every individual person in the experiment. So you probably want to treat those as random effects. But you would want to know, for example, how much variance is explained by the subjects that you tested in your experiment. So there are a few more advantages of mixed effects models that we haven't yet covered. One is that they can handle missing data. If you have any data missing and you want to run an ANOVA, even if you have only one cell missing for a subject, you lose that whole line of that subject's data. Mixed effects models can also handle complex hierarchical or multi-level structures, and they can also handle dichotomous outcome variables in addition to continuous outcomes. So in an ANOVA, we're assuming that effects are constant across individuals. We're assuming that every condition affects every person in the same way. And what this means that the random variation that is due to variability in the subjects is all mashed together in the error term that you get in the output. And all that you're doing with a mixed effects model is unpacking this error and helping to explain the individual variation in the model. Another question that people often have is, what does it actually mean when you say a random intercept and a random slope? So there are some great visualizations available, so we can look through what these look like in practice. Okay, so these visualizations will help us to easily understand what random intercepts and random slopes are, and we'll include the link in the write-up after this stream so you can look at those yourself. So in the example given here, the data belong to a nested structure. The researcher wants to estimate faculty salaries when the faculty work in different departments. So you could imagine that the department that a person works in might affect their salary. And here the different faculties are represented by different colors. So what we would typically do with a straightforward linear regression approach is to try to estimate the faculty salaries based on their number of years of experience. So we have years of experience along the x-axis and salary along the y-axis. And we're treating years of experience as a fixed effect because we're saying that the effect of experience is constant or fixed for each person. We can see that a relationship is there, but it's obvious that there's variation in the salary depending on the department that the person is in. So maybe it's the case that each department has a different starting salary for their faculty, but the annual rate at which the salaries increase is consistent for all faculties. If we think this is true, then we want to allow the intercept to vary by department, whilst assuming that the rate of increase is the same across departments. Alternatively, we can imagine that everybody starts on exactly the same salary, but the salaries increase at different rates depending on the departments. So we could then allow the slope to vary in the model whilst keeping the intercept fixed. But this is clearly a really poor fit for the data because fixing the starting salary means that the starting salary is highly inaccurate for most people and leads to the model assuming that salaries actually decrease over time for people in particular departments, which is obviously very unlikely to happen. So the most realistic scenario is one where the faculty salaries both start at different levels depending on department and also increase at different rates depending on department. So to incorporate both of these into the model, we want to allow both random slopes and random intercepts. And this clearly models the observed data the most accurately. So a question that people have is, do I always want to include random intercepts and slopes in my model? And in an ideal world, the answer is yes. You at least will always include random intercepts, otherwise all you have is fixed factors. The question of whether or not to include random slopes is one that's generated a lot of debate within this literature over the last few years. Dale Barb in 2013 published a really influential paper where he argued that you should keep it maximal. So always include random slopes for all fixed effects. The alternative to that would be a minimal model, which would just include random intercepts. And Barr's concern mainly was controlling type 1 error rate. So if you include random slopes, then you're minimizing the possibility of making a false positive. Then in 2012, a great book by Walter Stroop, he argued that neither the maximal nor the minimal linear mixed models are appropriate for most repeated measures analysis. Using the maximal model is generally wasteful and costly in terms of statistical power for testing hypotheses. And then on the other hand, the minimal model fails to account for non-trivial correlation amongst repeated measurements, and this results in an inflated type 1 error rate. But we can usually find a middle ground, a covariance model that adequately accounts for correlation, but is more parsimonious than the maximal model. And this allows us full control over type 1 error rates without needlessly sacrificing power. So Douglas Bates in 2015 and again in 2017 wrote that we maybe shouldn't always include every possible random slope into our model. He argued more for parsimonious mixed models, with the idea that this would balance our concerns about both power and about making a type 1 error. One problem, practical problem that you can encounter when trying to include random slopes in the model is that the model can fail to converge. So what this means is the way that linear mixed effects models estimate parameters is through a method called maximum likelihood estimation. This is an iterative procedure where the model is trying to find the parameter values that maximize the likelihood of making the observations. So if the model structure is too complex and you don't have enough data for the number of variables that you include, the parameter estimation can fail to converge, which means it fails to find a solution. And random slopes are the thing that vastly complicate the model structure and take up a lot of degrees of freedom, which is why if you don't have very much data, including random slopes can make it difficult for your model to estimate parameters. Another question that people often have is whether or not to add covariates into the model. And the answer to this question is that the usual rules apply and that you should do so with extreme caution. So my personal recommendation would be that you should only include critical and strongly hypothesis-driven variables. However, if you're doing a very exploratory study, then you probably would need to take a different approach. The general rule of thumb is that you will need at least 10 to 15 participants for every term that you include in the model. And remember that each main effect and interaction counts as a term. So if you have 2 factors and an interaction between them, you already need 30 to 45 participants. So that's probably a standard number of people in a psychology experiment. So covariates above and beyond that would need more participants. And if you include too many covariates into the model, then you risk overfitting, which means that the model does a perfect job of being completely tailored to the idiosyncrasies of this particular set of sample and items, but does a really poor job of explaining data from new subjects and items. And this means that all of your parameter estimates become really misleading and you can't generalize. So that's another argument against including too many covariates into the model.
You check whether we have questions because we can't see it right now. Whether people are commenting? No, that's fine. Right.
That's okay. And then one of the biggest questions of all is, how do I know when I run my analysis if my predictors are significant? Because the first time that you run a mixed effects model in R, you will notice that you don't get any p-values. This can be really disconcerting for us psychologists who are very reliant on p-values. And the reason that we don't get them is because to calculate p-values, you need to know the number of degrees of freedom, and it's really hard to work out what the number of degrees of freedom are in a mixed effects model when you have random intercepts and random slopes. So Steve and Luke last year published a great paper in Behavior Research Methods where he compared some different methods that people use to evaluate significance in linear mixed effects models. So the first way that people often use is to construct two models that are identical, except that one contains the term that you're interested in evaluating the significance of, and the other one does not. And then you would compare these two models using a likelihood ratio test. And if the test result is significant, then you know that the predictor significantly affects the model. Option number 2 is to use a rule of thumb. So on the whole, if the t-value is above around 2, then the predictor is probably significant. And option 3 is to try to approximate the degrees of freedom. So there is a package that you can load in R called LMER test, which uses a method of approximating the degrees of freedom. And the results of the analysis he conducted show that option 3 is the best. So approximating the degrees of freedom using the LMER test package in R is the best way to control the number of type 1 errors and know if the predictor is significant or not. And the good thing about this is that if you install this package, you don't need to do anything else. Once you run the model, you'll just get p-values there automatically. So I think that's most of what I wanted to say before we actually get stuck in and look at some data in R. So shall we have a look first at how people might structure their data before even getting to the R stage? That's not it. This one. Mm-hmm. So if you download the data from OSF, as Francisca showed you at the beginning, this is what this data looks like when you open it up. And the first column, the subject ID, you can see there's lots and lots of ones down here. And what this is telling us is that usually when we would construct an ANOVA, each row in our data would be a whole participant, all of the data from that participant averaged for each condition. But the way that we want to set it up for a linear mixed effects model is where each row in the spreadsheet is a trial rather than a subject. So here we know that for trial number 1, all of this information. And for every single trial number, we know exactly all the information about that trial. So do you maybe want to explain a little bit about what the study was?
So in the study, each of the subjects saw, I think, 80 images of faces, 40 of which were male and 40 of which were female. And before the face was presented, people saw a name, which could be of 2 categories. Either it was a front vowel name or a back vowel name. And the hypothesis was that maybe women are rated as more attractive when they're paired with one class of name, whereas males are more attractive when they're paired with another class of names. So the idea was that for some people, a Tim might be hotter than a Tom, and for another group of people, maybe the other way around. So what we have here is one column with the subject ID, which goes through all the subjects. Then I have the gender of the writer, the age of the writer, the trial number, which is continuously numbered, the name, which is basically just the item variable, or the item for the name. And the only thing which is important in this column is that that each item has a unique name and it's repeated across over subjects. So this is the only thing which actually matters here. Same for pictures. These just have to be individual names which are unique. unless you present the same stimulus multiple times. Then the gender of the person who was depicted, the vowel condition, whether it was a front or a back vowel, and response key is the measure. So after the person, after our subject saw a face, they rated the face of how attractive they find the person, and whether they want to go to drink a beer with that person or not. So yeah, if we now load this data in the R Studio, I have to swap screens. Yes. All right. So now when we load this data in R Studio, I first give a quick walk around the R environment. And also the name of the data file which you downloaded is slightly different than the name I have here in my code. So please adjust this when you're calling the data file. So, but first things first, this is how R looks like, R Studio, when you open it. This is your editor window where you can add all your code. And this is also where you can copy paste everything I have in the data script, which I uploaded into, and you only change this part so that it matches the file name where your data is in. This is your console, or yeah, basically where you can try out things and where the output is presented. Here, it loads your data and the objects you're loading, and here you have plots and files you're exporting. The first thing you do when you open R is you set your working directory. It's very important that in this directory, the file in which the data is saved. And the file should always have a comma-separated value ending, because R can best deal with this type of files. So make sure that if you have an Excel file with your data in it, that you use the save as function and export it as a comma-separated value file. So then you read in, once you have set the working directory, you're reading in the data. And then you can see here, I now have a new object, which is called Tim Data. And when I open it, I have my CSV file with all the contents I want. In the next step, we are calling all the packages we want. If you're using R for the first time and you don't have the packages we're using installed already, you use the command install package, and then you put your package here, like I have, like this one. Basically, you just mark the row in which the code is, and then you press run. Great. So this was a bit useless because I already had it installed, but we can now call all the libraries we want. So once you have installed your package in our environment, you just call the library whenever you want to use it. And then R works on this. The next thing you want to do is, even though R often does this automatically and very nicely, sometimes things go wrong. So you want to code all the factors and variables you're interested in as factors or as measures. So every column which has a header here is marked here. This refers to the data frame. This is the column I'm interested in, and this is how I name the variable. I always keep them identical to avoid pointing errors, but you don't have to do this. You can name this as you want, as long as you have here exactly the same combination as here in the header of your column. So everything which is a factor and not a natural number, you code as a factor. Everything which is numeric, you code as numeric. This makes a difference in how this data is dealt with. Especially with things like response keys or scales instead of like rational scales, like temperature or or reaction times, it's very important to center the scale and rescale it. So I'm now going to do this for my measurement, which is the response key, and this is how the subject have rated this. I put a bunch of explanations here, which are in the code. This is supposed to help you at the end of the day when you have to deal with this your own. So now we're building a model. We're building a first simple model, which is called attractiveness. We're calling the linear mixed effect regression function, and we model response key because this is our outcome variable where we're interested in. Each of the factors which we use as predictors for the model are then added. If you want factors to interact, you put a star in between. If you enter them separately, you put a plus between the factors. Random effects are in brackets, and random effects with only a random intercept are coded with a 1, and then this bar, what's this thing called?
I don't know. Yeah.
Well, this straight line, and then the name of the variable. And if you have random slopes, you have the random factor plus the variable for which you want to allow random slopes. And you can also do both. This would look like this. And you have random intercepts and slopes. And yeah, basically, this is already the model. At the end, you have comma and then refer to the data frame. And then whether you want to apply the maximum likelihood criterion. I strongly recommend, if you're playing around, to always set this on true instead of false. False is great if you're doing very complicated models, and especially if you do computational modeling or have a lot of computing power at hand and you really want to have the perfect model. But it really estimates all possible models, I think. So what happens is that your computer will be busy for several hours and you won't be able to do anything. So be careful with this option. So now we run our first model and look at the output. The model is done. You can, and if we want to see the output of the model, we call the summary of the model. And this is how the output of a linear mixed effect model looks like.